はい、それでは時間になりましたので、次のセッションは、加藤公和さんによる Effective Numerical Computation in Numpy and Scipy です。じゃあ拍手の方はよろしくお願いします。どうぞよろしくお願いします。
So my talk is titled Effective Numerical Computation in Numpy and Scipy. So I will start with asking a question. Anybody here have experiences in Numpy? Raise your hand. Okay, so the second question. Uh, Anybody here uses Numpy on a daily basis? Raise your hand. Few. All right, that's great. Sorry. So, I'm trying to be. I will try to be beginner friendly anyway. So let me introduce myself. My name is Kimikazu Kato, a chief scientist at Silver Technology, and got PhD in computer science. My expertise is in mathematics, numerical computation, algorithm, and so on. To tell the truth, my career as a Python programmer is not so long. So I changed my job about 2 years ago, and I started using Python after that. But even before that, I used other languages to solve numerical mathematical issues. I have more than 10 years experience in numerical computations. Now my main job is designing algorithms for recommendation system, and also doing some research about the machine learning and data analysis. So this talk is about effective usage of Numpy and Scipy, especially about the computational speed. And this is not all-inclusive introduction of the capability of Numpy and Scipy, and just shows some interesting topics according to my experience. And this is the outline of my talk. So anyway, the main part is about sparse matrix and the case studies. But before that, I don't regard everybody knows about Numpy, so I will introduce some basic capability of Numpy, especially two very powerful tools, broadcasting and indexing. So what is numerical computation? Or in other words, we also say numerical analysis. This is just a list of what comes to my mind. This is not all, but for example, differential equation, simulations, signal processing, machine learning, etc., are called numerical computation. And about numerical computation, many people use C or Fortran or other lower level languages. So, but why do we use Python in numerical computation? One reason is its productivity. It's easy to write and easy to debug. There's no segment fault, and there's no implicit memory destroy, and so on. That's one good big merit. Another merit is the connectivity with visualization tools, especially Matplotlib and IPython you saw in the previous talk. And last one is related to my job. So we are providing the recommender system. So it's important to connect with web system. And Python has many good web frameworks like Django or Pyramids. So these are merits of using Python in numerical computation. But okay, so Python is easy to use and easy to debug, but Python is very slow, isn't it? Why do you use Python in numerical computation? This is the example. Upper one is written in C, and the one below is written in Python. They are doing the same thing. They are just computing the sum of the 1 to 100 million. But the code written in C takes only 0.1 second. But code in Python takes about 80 seconds. So more than 80 times slower. So if you are experiencing NumPy, you can say this is stupid because this is not good code. But as I said, my experience in Python is not so long. So I remember when I was a beginner. So at first, I thought Python was garbage because of this kind of experience. So you have to know what is the good code. This is a better one. It takes about 0.18 seconds. You should use a range of NumPy. It generates the sequence from 1 to 100 million. If you use it, it's very fast. Still slower than C, but C is about, code written in C takes about 0.10. So I think this is not so bad. If you say this is very slow still, you should use C. But I think this is good. So with this very, very simple example, we can learn some things. First, person is very slow when written badly. So when written badly is very important. And another lesson is translate C code into Python directly is often a bad idea. However, you can rewrite the original algorithm into Python-friendly manner. Sometimes the performance improves drastically. So even with that simple example, we can learn these things. And about the practice to improve about the practices for the performance improvement, we can learn things even from that simple example. First, anyway, you should avoid full sentence as far as possible. Full sentence is very slow. And utilize libraries capability instead. In that example, I used a range and sum method. That makes it much more faster. And third practice is forget about the cost of memory copying. Typical C programmer might care about that. But if you need to copy the memory to utilize the library, you should do that. In that simple example, using a range occupies much more memory than using for, because it generates the array. But it is better in the world of Python. C programmer might hate that, but in Python, that is good practice. So now I will talk about basic techniques for NumPy. As I said, this is not all inclusive, just introducing some examples. Oh, sorry, there's no figure. So broadcasting is a technique to apply. Broadcasting is a technique to apply operation to an array. So sorry, there's no figure. So it's explaining the idea. But if you use a multiplied by 3, so a is the array, then each element is multiplied by 3. And the second example is about square root. So when b is array and you take square root of array, then you take each element of square root. So this kind of function is called universal function. So as a definition, function which is related to each element when applied to an array is called universal function. And another technique is broadcasting. And A is applied to, so in this case, A is a 3 by 3 matrix, and B is size 3 array. And if you multiply A by B, first column is multiplied by first element of B, and second column is multiplied by second element of B, and so on. Important thing is, anyway, 4 sentence is evil. The same thing can be done with 4 sentence, but this is much faster. And another powerful technique in Numpy is indexing. Indexing is assigning the value to at multiple positions. In this example, A is set as an array. A is set as an array, and the indices are set as the array of the indices. Then, if the indices is in the bracket, you can set the same value to the multiple positions. In the first case, it's assigning 0. And second case, it's assigning another array. Then, so in the second example, multiple positions are modified. So this is anyway. This is not all inclusive. So we show some references. First one is mostly. First one is for beginners. It's more inclusive, I think. And second one includes more tricky techniques, very interesting things. It's available in the web. So just Google it. Just Google it with Numpy medkit. So now I will explain about sparse matrix. Sparse matrix is defined as a matrix in which most elements are 0. So most of the elements are 0. It can be expressed as a compressed way. So you don't have to remember 0 elements. So you just remember non-zero elements. In that compressed structure, it will be space effective and time effective. And the Python Scipy has a module for class for sparse matrix. There are some there are some classes to express sparse matrices, but so not here. I show three types of matrix. One is LIL matrix. It is convenient to assign a data. And CSR and CSC is mainly for computation. So usually when you use sparse matrix, you set data to LIL matrix. After that, you convert it to CSC or CSR matrix, and then you do multiplication or that kind of thing. This is a typical use case of using sparse matrix. First, you prepare LIL matrix as A, then assign data for non-zero element. Here, I just said 2 elements. After that, convert it to CSR matrix. If you say print A, it only shows the non-zero elements. But if you convert to a dense matrix, it can be shown as a usual matrix. And here, setting B similarly. And after that, this is the example of multiplication. So this is A times B. This is taking a product of A and B. And if you want sum of A and B, you just say A plus B. Then you can compute A plus B. So important point is LIL is convenient to assign a data. But to compute it, you have to convert it to CSR or CSC. And sorry again, there's no image. So this shows internal structure of CSR matrix. I think it's hard to explain without image, but I try. Anyway, this is what is expressed. In CSR matrix, data is stored in this way, this order. But it only has to remember non-zero elements, so they are skipped. This one are remembered, so like this. So the attribute data have these values. The attribute indices mean which column it belongs to. One belongs to column 1. So column starts from 0. So this is column 1, column 2. So 1 is started in column 1, 2 is started in column 2, and 3 is in 2, and 4 and 5 are started in column 0 and 1. And B in PTR, in pointer, is expressing from where to where is in given row. In this case, In this case, In this case, index 0 to 1 means the first row. I mean, so this means first two elements belong to first row. So index to 2 belongs to second row. It means only one element belongs to second row, and so on. This is the internal structure of CSR matrix. And about CSC matrix, it's mostly the same. It's symmetric to CSR, so I think I don't have to in detail. But the one different thing is it's stored in this order. I mean this order. 4, 1, 5, 2, 3. So this order. in CSR, it is stored in this order, but CSC stored in this order. And other things are all the same as CSR. So I explained the internal structure of CSR and CSC structure, CSC matrix. But what is it for? You might wonder. It's not. You don't have to understand the internal structure because, as I showed in use case, you can use it as a black box. Just set LIL matrix and convert it to CSR or CSC. It's enough. But there's one immediate merit because setting LIL is very slow. If you know the internal structure of CSR or CSC, and you can set directly into the internal structure, it's much faster than using LIL. So this is a benchmark of this kind of matrix. Look at this. Look at this matrix. It has two in the diagonal and one in the next to the diagonal. And this code explained sending the this is just setting the matrix. It's not computing. It's just setting this matrix. First one is setting to LIL matrix. Code is very simple. Second one is using internal structure to set CSR matrix. The code is a bit complicated. Then take the benchmark. The result is this. LIL takes about size is 10,000. So 10,000 by 10,000 sparse matrix with about maybe 20,000 non-zero elements. Then it takes about 11 seconds for LIL matrix. But for CSR matrix, it only takes about 0.05 seconds. Important thing is they are doing the same thing, just setting sparse matrix. So anyway, when you deal with already stored data, setting CSR or CSC directory is much faster. But code tends to be more complicated, so it depends on the cases, I think. So I showed case studies. Maybe I am running out of the time, so I wonder if I can show all of them. So first is the norms. Computing norms is also important in numerical computation. First, it's just computing the norms of usual vector. It can be computed with matrix product. Second one is about sparse matrix. I would say V is sparse vector, but there's no sparse vector type in Python, so it is expressed as 1 by n sparse matrix. In that case, this is good code. The difference is it's not using the matrix product, because if you take the transpose of the sparse matrix, the type of the matrix change, then the multiplication takes a long time. And this is the example of the Frobenius norm. I think it's obvious. Second case is about the applying universal function. For dense matrix, applying universal function is very easy. if you want to take tan h, I mean that means hyperbolic tangent of usual. You want to take tan h of usual dense matrix. You just say tan HA. It computes the tan h of each element. But same thing cannot be done for sparse matrix. It fails with error. This is natural because usually, if you are given, arbitrary function is not. If a function is given, the application of function cannot be sparse, necessarily sparse. But if that function satisfies 0 at 0, takes 0 value at 0, the density is preserved. So, for example, tan h is 0 at 0. It can be applied to sparse matrix theoretically. But as a capability of sparse, SciPy sparse, it is not allowed. So how can we compute it? Using 4 sentences is out of the question, of course. So you know the internal structure of sparse matrix, you can use that. But the position of non-zero elements is not changed even after the application of universal function. So all you have to do is just apply universal function to the all elements. So CSC or CSR matrix is expressed as data, expressed with a tuple of data indices and in the pointer. So all you have to do is just apply function to data. This is the solution. Maybe I'm running out of the time. So, maybe there's enough time to explain this example. So I just show. Okay. So I just explained the problem. This problem is written in the certain paper. A is given a dense matrix, and D is diagonal matrix. But the D is expressed as an array, usual array. Then how can we compute this formula effectively? In this case, first solution is using another sparse matrix type, diagonal type, to compute it. Another solution is to use internal structure. The last one is very simple, but it needs some mathematical derivation. It can be regarded as broadcasting. Then the code itself is very simple. And frankly, the result of the benchmark is not significant, I think. There's no significant difference between them, but last one is the most simple and fast. So last one is, I think, best. So this is conclusion. Anyway, try not to use 4 sentences. Instead, you should use libraries capabilities. And knowledge about the internal structure of sparse matrix is very useful to extract performance. And anyway, mathematical derivation is important. So you have to know the mathematics and the Python at the same time. You can list up the mathematically equal formulas. Then you can choose most Python-friendly formula. And last one is most important, I think. Computational speed sometimes not necessarily matters. So if you have to take a long time to have a good code, you should write a working code anyway. So if you can you can find a good code in a short time, it is valuable. So it depends on, anyway, it depends on situation. So this is the end of my talk. Thank you. And I'd like to thank Shimashima-san. Thank you.
どうもありがとうございました。時間が押しておりますので、もしご質問があれば、一つだけ一問だけ大丈夫ですけれども、ご質問はありますでしょうか。はい。
The topic about the sparse matrix is very interesting for me. Thank you very much. And I understand the CS matrix is very effective for the matrix operation. Do you know the linear algebra routine for the linear algebra problem, such as the eigenvalue problem, or linear equations. The solver of the linear eigenvalue problem, or
so your question is there any good eigenvalue solver for the sparse matrix?
Yeah.
I don't know. Sorry.
Are there in the Scipy?
Maybe there's one, but I haven't used one. Sorry.
Oh.
I have no experience.
Thank you.
それじゃあ加藤様どうもありがとうございました。
There's no figure, so